Hello, in this lecture we will find the length of chord AB. In the drawing we have a semicircle, and inside this semicircle we have three circles. Those two small circles are identical, and the middle circle is tangent to the semicircle at point O, and point O is also the center of this semicircle, and we know that PQ equals to 8 units. So actually PQ is the diameter of this semicircle, and the diameter of any circle is twice as large as the radius. So if the diameter PQ of the semicircle equals to 8 units, then the radius will be equal half of it, that is to say it will be equal to 4 units. Therefore the radius PO will be equal to 4 units, and the radius OQ of the semicircle will be also equal to 4 units, and the radius OX of this semicircle, it is also equal to 4 units, but the radius OX of the semicircle, it is also the diameter of this middle circle. So we know the diameter of this middle circle equals to 4 units. Therefore the radius of this middle circle will be equal half of it, that is to say it will be equal to 2 units, that is to say CX, that is the radius of the middle circle, will be equal to 2 units, and OC, that is also the radius of the middle circle, will be also equal to 2 units. And we will join together, we will define the center of this small circle as M, and we will join together the centers of the small circle and the center of the middle circle. So MC, line segment MC, it is actually the distance between the centers of those circles and the distance of the distance between the centers of two circles that have an external lunge between them. Like in this case, those two circles are tangent to each other at this point. That is the point of tendency. We will define the point of tendency between those two circles as point Y. So when we have two circles that have an internal and external lunge between them, like in this case, then the distance between their centers will be equal to the sum of their radiuses, or to the length of the to the sum of the length of their radiuses. So if we define the radius of this small circle as R, so My will be equal to R, and we already know that the radius of this middle circle equals to 2 units. So in total we will get that MC, that is the distance between the centers of those two circles, will be equal to R plus 2. And we have here actually PQ. We can also call it tangent PQ, is tangent to this small circle at this point. This is actually the point of tendency. So we will define this point as point N. And we will join points M and N together by a straight line. Actually, MN is the radius of this small circle because of the fact that it starts from the center of this small circle and ends at a point N that is a point on the circle itself. Therefore, MN is the radius of this small circle, that is to say it equals to R. And we actually have a rule that states that whenever we have a radius that is drawn to the point of tendency, like in this case, the radius Mn, it is actually drawn to the point of tendency. You can see here, this radius, the radius Mn, it is drawn to the point of tendency, that is to say, it is drawn to point N, that is the point of tendency of tangent PQ with this small circle. Therefore, according to that rule, the tangent PQ will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees. Likewise, we have the radius CO of this middle circle that is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent PQ with this middle circle. The point of tendency is point O, and this radius, the radius CO, it is drawn to the point of tendency. Therefore, the radius PQ will be perpendicular to this. Therefore, the tangent PQ will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay. In the next step, we will draw a perpendicular from point M, from this point M, to CO. We'll draw perpendicular from point M to CO, and we will define the touching point between the perpendicular to CO as point D. So MD is perpendicular to CO, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay. And we also know that AB is parallel to PQ. Again, AB, the chord that we are looking for, AB is parallel to PQ, and we have a rule that states that corresponding angles between parallel lines are equal to each other. So angle POE, this angle is equals to 90 degrees, and it must be equal to this angle according to the rule that corresponding angles between parallel lines are equal to each other. So, because of the fact that AB is parallel to PQ and those two angles are located between the parallel lines AB and PQ, and therefore they are equal to each other, and if this angle equals to 90 degrees, then this angle will be also equal to 90 degrees. Okay, again, I repeat again that those two angles are located between the parallel lines AB and PQ, therefore they are equal to each other. That is to say, if this angle equals to 90 degrees, then this angle also equal to 90 degrees. And we will define this point as point E. So I will draw the quadrilateral MNOD and the triangle, the right triangle MCY. Actually, we will I'll draw it again in a new page. So we have the quadrilateral NODM, so I actually draw again the quadrilateral MNOD and the two right triangles, triangle CEY, in the right triangle, triangle CMD. So here in quadrilateral MNOD, we have three right angles, and we have a rule, I will call it rule number 1, that states that the sum of the angles in any quadrilateral is equal to 360 degrees. The sum of the angles in any quadrilateral is equal to 360 degrees. So I will repeat again on rule number 1. According to rule number 1, the sum of the angles in any quadrilateral is equal to 360 degrees. And especially in quadrilateral MDNO, in quadrilateral MDNO, the sum of its angles must be equal to 360 degrees in this quadrilateral. So here in quadrilateral MDNO, we have 3 right angles, 1, 2, 3, and the sum of them is 90 degrees times 3 is equals to 270 degrees, plus the fourth angle. We will define this angle, that is the fourth angle of quadrilateral MDNO as angle X, plus, so 270 degrees, plus the size of the fourth angle, angle X, must be equal to 360 degrees according to rule number 1 that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we will subtract 270 degrees from this equality, and we will get that angle X equals to 360 degrees minus 270 degrees. It is actually 90 degrees. So we found out that angle X is a right angle, it equals to 90 degrees. So we write here that angle X is a right angle, it equals to 90 degrees. So as you can see from the drawing, quadrilateral MDNO, this quadrilateral has 4 right angles, and we have rule number 2 that states that any quadrilateral that has 4 right angles must be at least a rectangle. I will write down the rule number 2. According to rule number 2, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So I will read rule number 2 again. According to rule number 2, any quadrilateral that has 4 right angles must be at least a rectangle. Therefore, quadrilateral MNDO must be a rectangle if not a square. Okay, it either could be a rectangle or a square. Okay, so we will consider it as a rectangle. Okay, so here we know that angle that MN, it is actually the radius of the small circle. So here MN equals to R, it is the radius of the small circle. And we have rule number 3. According to rule number 3, the opposite sides of a rectangle are equal to each other. I write it down. According to rule number 3, the opposite sides of a rectangle are equal to each other. I will read rule number 3 again. According to rule number 3, the opposite sides of a rectangle are equal to each other. So here, side MN of rectangle MDNO must be equal to side DO, because MN is the opposite side of DO. So MN equals to DO according to rule number 3. We'll write it down. MN is equal to DO according to rule number 3. Again, MN equals to DO according to rule number 3, that the opposite sides of a rectangle are equal to each other. But we know that MN equals to R, it is the radius of the small circle. MN equals to R, it is actually the radius of the small circle. So from this equality, we will conclude that DO also equals to R. DO equals to R. I'll repeat again. From this equality, we will conclude that DO also equals to R. So here, DO equals to R. It is the radius of the small circle. Equals to the radius of the small circle. And we also know that CO is the radius of the middle circle. I'll repeat again here. CO, this line segment CO is the radius of this middle circle. That is to say, it equals to 2 units. So we write here that CO, that is the radius of the middle circle, it equals to 2 units. CO equals to 2. So, what is the value of CD? The value of CD equals to CO minus DO. Again, CD equals to CO minus DO. I will write it down. CD, its line segment, equals to CO minus DO. Okay. CD equals to CO minus DO. But we know that CO equals to 2 units. It is the radius of the middle circle. It equals to 2 units, and DO is the radius of the small circle, that is to say it equals to R. So in total we found out that CD equals to 2 minus R. Again, CD equals to 2 minus R because it equals to CO minus DO. CO equals to 2 and DO equals to R. In total we found out that CD equals to 2 minus R. Okay, CD equals to 2 minus R. We can write here that CD equals to 2 minus R. And we have already found out that MC, that is actually the distance between the centers of the small circle and the middle circle, MC equals to the sum of the lengths of the radiuses of those circles, that is to say it equals to R plus 2. So MC, that is the distance between the centers of the two circles, is equal to R plus 2. MC equals to R plus 2. Okay, so here we'll focus on the right triangle, triangle CDM. Okay, in the right triangle, triangle CDM, according to the Pythagoras theorem, that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. In our specific right triangle, it means that the square of the hypotenuse is cm, therefore the square of the hypotenuse, it is cm squared, equals to the sum of the squares of the perpendiculars. It equals to CD squared plus MD squared. I'll repeat again. If we relate to the right triangle triangle CDM, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is cm square, and it equals to the sum of the squares of the perpendiculars. That is to say, it equals to cd square plus md square. But we have already found out that cm equals to r plus 2. If cm equals to r plus 2, then cm square will be equal to r plus 2 square. So r plus 2 square equals to cd square. We have already found out that cd equals to 2 minus r. So if cd equals to 2 minus r, then cd square will be equal to 2 minus r square plus md square. I'll repeat again. Cm equals to r plus 2, so cm square will be equal to r plus 2 square. Cd equals to 2 minus r, therefore cd square equals to 2 minus r square, and md square equals to md square. Here we will open the brackets of this equation number 1, and we will get that r plus 2 square equals to r square plus 4r plus 4, and it is actually equals to it equals to 2 minus r square. 2 minus r square is 4 plus r square minus 4r. And here we have md square. We will leave it as it is. So after we open the brackets in this equation number 1, we got to this expression. So here we have r square in both sides of equation number 1. So r square will get cancelled. And we also have 4 in both sides of equation number 1, so 4 will also get cancelled. So what is left from equation number 1 after we cancelled those expressions? What is left from equation number 1 is actually 4r equals to minus 4r plus md square. So here we will add 4r to this equation number 1, and we will get that 4r plus 4r is 8r. 8r equals to minus 4r plus 4r is 0, so 8r equals to md square. Here we will take a root out of this equation number 1, and we will get that md equals to the square root of 8r. We know that 8 equals to 4 times 2, so we will substitute 8 by 4 times 2, and we will get that MD equals to the square root of 4 times 2 times R. The square root of 4 is 2, so I write it down. In total, we got that the value of MD, or the length of MD, it is equal to 2 times square root of 2R. We found out that MD equals to 2 times square root of 2R. Okay, so we can write here that MD equals to 2 times square root of 2R and we have rule number 3 that states that the opposite sides of a rectangle are equal to each other. So in our rectangle, it means that MD equals to NO. According to rule number 3, MD is equals to NO. I will repeat again. In our rectangle MD and O, the opposite sides are equal to each other. It means that MD equals to NO, according to rule number 3. But we have already found out that MD equals to 2 times square root of 2R. MD equals to 2 times square root of 2R. So from this equality, we will conclude that NO also equals to 2 times square root of 2R. NO equals to 2 times square root of 2R. So we can write here that NO also equals to 2 times square root of 2R. Okay? In the next step, we will connect together, we will join together points M and O by a straight line. And we will also connect together points G, M, and O in our original drawing by a straight line. And we will also connect together points A and M by a straight line. So what is AM? AM, as you can see, AM, it is a line segment that starts from the center of the small circle, that is to say from point M, and ends at point A, that is a point on the circle itself, or the small circle itself. Therefore, AM is equals to R. It is the radius of the small circle. AM equals to R, it is the radius of the small circle, and we know that OA is the radius of the semicircle, that is to say, it equals to 4 units. OA equals to 4 units. It is the radius of the semicircle. And what is the value of MO? The value of MO is actually OA minus MA. OA minus MA equals to OM. OA minus MA equals to OM. I'll repeat again. OA minus MA equals to OM. But we know that OA equals to 4 units. It is the radius of the semicircle, and MA, it is the radius of the small circle. It equals to R. So in total we found out that OM equals to 4 minus R. Okay? I'll repeat again. OM equals to OA minus MA, and OA equals to 4 units, and MA equals to R. So in total we found out that OM equals to 4 minus R. So we can write here that OM equals to 4 minus R, and we can also write here that OM, this line segment, equals to 4 minus R. So in the next step, we will focus on the right triangle, triangle MNO. This right triangle. So on the right triangle, triangle MNO, the right triangle in the green color, triangle MNO, according to the Pythagoras theorem, in the right triangle, triangle MNO, the green triangle, according to the Pythagoras theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green right triangle is MO, therefore the square of the hypotenuse is MO square. MO square, and it equals to the sum of the squares of the perpendiculars. This is to say, it equals to MN square plus NO square. So I will repeat again. In the right triangle, right green triangle, triangle MNO, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, MO square equals to MN square plus NO square. But we've already found out that the value of MO is 4 minus R. If MO equals to 4 minus R, then MO square will be equal to 4 minus R square. And it equals to, so MO square equals to 4 minus R square, and MN equals to R. If MN equals to R, then MN square will be equal to R square plus NO square. We have already found out that NO equals to 2 times square root of 2R, and NO square will be equal to 2 times square root of 2R square. So in total, we found out that 4 minus R square equals to MN square, it is R square, and NO square, it is 2 times square root of 2R square. Okay, here we will open the brackets in both sides of this equation number 2, and we will get that four minus R square is actually 16 plus R square minus 8R, and it equals to R square plus 2 times square root of 2R square is 8R. So here we have R square in both sides of equation number 2, so R square will get cancelled. And what is left after we cancelled, what is left of equation number 2 after we cancelled R square? Before that, first of all, we will add 8R to this equation number 2, and we will get that 16 equals to 8R minus 8R is 0, so here is only 16 left in this side of the equation number 2, and on the other side of the equation number 2 we have 8R plus 8R is equals to 16R. So here we will divide equation number 2 by 16, and we will get that R, the radius of the small circle, equals to 1 unit. R equals to 1 unit. So here R equals to 1 unit. R equals to 1. We know that CD equals to 2 minus R, and R equals to 1, so CD will be equal to 2 minus 1, that is 1. So CD equals to 1, and R also equals to 1. In the next step, we will focus on those two right triangles, on the right triangle, triangle CEY, and on the right triangle, triangle CDM, and we will actually prove that those two right triangles are similar to each other. Okay, so we will focus on the right triangle, triangle CEY. And on the right triangle, triangle CDM. This right triangle. I will repeat again, we will focus on the right triangle, triangle CEY, and on the right triangle, triangle CDM. we'll prove that those two right angles are similar to each other. First of all, those two angles, they're equal to each other, they are both right angles. So angle CEY into angle CEY is equal to angle CDM into angle CDM, and both angles are equal to 90 degrees, they are right angles. I will repeat again. Angle CEY is equal to angle CDM, and they are both equal to 90 degrees, they are right angles. And we also know that this angle angle C, is a common angle. It belongs both to triangle CEY, and angle C also belongs to triangle CDM. So we can write down that angle C equals to angle C is a common angle that belongs to both triangles. Angle C equals to angle C is a common angle that belongs to both triangles. I'll repeat again. Angle C equals to angle C. It is a common angle that belongs to both triangles. And we also have those two angles, they are equal to each other according to third angle theorem. So this angle, that is angle CYE, in triangle CYE, is equal to this angle CMD on triangle CDM, angle CMD, and they are equal to each other according to third angle theorem. I will repeat again. Angle CYE equals to angle CMD. They are equal to each other according to third angle theorem. So what is third angle theorem? Third angle theorem is that if two angles in one triangle congruent to two angles in another triangle, then the third pair of angles must also congruent. I'll repeat again. If two angles in one triangle congruent to two angles in another triangle, then the third pair of angles must also congruent. And here we actually proved that those two angles are equal to each other, and we also have, so those are the first pair of angles that congruent, and we have here a common angle that we can say that this angle equals to itself. So this is the second pair of angles that congruent in those triangles, and therefore, according to third angle theorem, the third pair of angles, this third pair of angles must also congruent. That is to say, this angle equals to this angle. So this is the third angle theorem. So we actually proved that all three angles 1, 2, 3 of triangle CY congruent to all three angles of triangle CDM. Therefore, we actually proved that triangle CYE is similar to triangle CMD according to angle similarity rule. So I will write it down. We actually proved the triangle CYE we proved the triangle CYE is similar, this is the sign of similar to triangle CDM according to angle similarity rule. I'll repeat again, we proved that triangle CYE is similar to triangle CDM according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle can point to all three angles in another triangle, then you actually prove that those two triangles are similar to each other according to angle similarity rule. So from the fact that angle and the triangle CEY is similar to triangle CDM, we will conclude that the following equality is true. We will conclude that CE over CY in triangle CEY CE over CY in triangle CYE equals to CD over CM in triangle CDM. So I will repeat again, from the fact that triangle CYE is similar to triangle CDM, we will conclude that CE over CY in triangle CYE equals to CD over CM in triangle CDM. Okay, so CE over CY. What is the value of CY? As you can see from the drawing, CY equals to 2 units. It is the radius of the middle circle, so CY equals to 2 units, and it equals to CD. You can see here that CD equals to 1 unit. CD equals to 1 unit over CM. You can see here that CM equals to R plus 2, and we have already found out that R equals to 1, therefore CM equals to R plus 2, that is to say it equals to 1 plus 2, that is actually 3. So CM equals to 3 units, so it is 1 over 3. In total, we got that CE over 2 equals to 1 over 3. Here we'll multiply this equation number 3 by 2, and we will get that CE equals to 2 over 3. CE equals to 2/3. So here we can write down that CE equals to 2/3. CE equals to 2/3. And you can see from the drawing that CD minus CE equals to DE. Again, CD minus CE equals to ED. CD minus CE equals to DE. CD minus CE equals to DE. That is to say, DE equals to CD, that is 1, minus CE, that is 2/3. 1 minus 2/3 equals 2/3. So we found out that DE equals to 1 minus 2/3, that is third. We can write here that DE equals to third. DE equals to third. So here we can write that DE or ED equals to third. And what is the value of OD? What is the value of OE? The value of OE, you can see that the value of OE, it is actually OD plus DE. OD plus DE. So we can write here that OE equals to OD plus DE. OE equals to OD plus DE. So OE equals to OD. OD equals to 1 plus DE equals to third. So OE equals to 1 plus third, that is to say it equals to 4/3. So OE equals to 4/3 units. OE equals to 4/3 units. So we can write here that OE, this line segment OE, equals to 4/3 units. Okay? In the next step, we will connect points O and B by a straight line. We connect together points O and B by a straight line. And we will find out the size of angle OED, the size of this angle, angle OED. So we actually know that AB is parallel to PQ. It is given us the question that AB is parallel to PQ. And we actually have a new rule. Actually it will be rule number 4. according to rule number 4, the sum of two one-sided angles between parallel lines is equal to 180 degrees. Okay, according to rule number 4, the sum of two one-sided angles between parallel lines equals to 180 degrees. I'll read rule number 4 again. According to rule number 4, the sum of two one-sided angles between parallel lines equals to 180 degrees. So here we know that AB is parallel to PQ. AB is parallel to PQ. Therefore, the sum of those two one-sided angles that are located between the parallel lines AB and PQ must be equal to 180 degrees. That is to say, this angle that equals to 90 degrees plus the size of this angle that is actually angle OED, angle OEB. The sum of those two angles must be equal to 180 degrees according to rule number 4. I will repeat again. We know that AB is parallel to PQ, and therefore the two one-sided angles that are located between the parallel lines AB and PQ must be equal to 180 degrees. And the two angles that are located between the two one-sided angles that are located between the parallel lines AB and PQ are: the first angle is an angle that equals to 90 degrees, and the second angle is angle OEB, and according to rule number 4, the sum of those two angles must be equal to 180 degrees. So here we will subtract 90 degrees from this equality, and we will get that angle OEB equals to 180 degrees minus 90 degrees. It equals to 90 degrees. So we found out that angle OEB is a right angle. It equals to 90 degrees. So this angle OEB, it is a right angle. It equals to 90 degrees. And if this angle is a right angle, then triangle OEB is a right triangle. So I will copy again this right triangle, triangle OEB, and we will find all the sides of the right triangle, triangle OEB. So we have the right triangle, triangle OEB. So we found out that angle OEB is a right angle, it equals to 90 degrees. We have already found out that side OE equals to 4 over 3 units, and OB it is the radius of the semicircle, therefore it equals to 4 units. Okay, and the only thing that is left to do is to find out the size of the length of side EB of the right triangle OEB, and according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is OB, so the square of the hypotenuse is OB square. And it equals to the sum of the squares of the perpendiculars. That is to say, it equals to OE square plus EB square. So I will repeat again. According to the Pythagoras theorem, in the right triangle OEB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OB square equals to OE square plus EB square. But we know that OB equals to 4 units, therefore OB square is 4 square, 4 square is 16. And it equals to OE square, that is to say it equals to 4 over 3 square plus EB square. Okay? So we found out that 16 equals to 4 over 3 square plus EB square. Here 4 over 3 square, it is actually 16 over 9. So I write it down. Sixteen equals to 16 over 9 plus EB square. We will subtract 16 over 9 from this equation number 4, and we will get that 16 minus 16 over 9 equals to EB square. Here we will multiply 16 by 9 and then we will divide it by 9 in order to have a common factor with 16 over 9. So we get that 16 times 9 over 9 minus 16 equals to EB square. So here (16 times 9 minus 16 is 16 times 8). So I write it down. (16 times 8 over 9 equals to EB square. So here 16 is 2 times 8. So we'll substitute 16 by 2 times 8. And we'll get that 2 times 8 times 8 over 9 equals to EB squared. So here we will take a root out of this equation number 4, and we will get that EB equals to the square root of 2 times 8 times 8 over 9. And the square root of 8 times 8 is 8, and the square root of 9 is 3, so we write it down. We got that EB equals to 8 over 3 times square root of 2 units. We found out the value of EB. EB equals to 8 over 3 times square root of 2 units. So in the next step we will prove that those two right triangles can go into each other. So we will actually prove that the right green triangle OEB is congruent to the right green triangle OEA. Okay? So I will copy those two right triangles and we will prove that they can go into each other. So we have so we will actually prove that those two right triangles can go into each other, or triangle OEB is congruent to triangle OEA. So we know that OA equals to OB equals to 4 units. OA equals to OB equals to 4 units. So the hypotenuse in those triangles are equal to each other. And OA is a common side, it belongs to both triangles, so we can write down that OE equals to OE is a common side that belongs to both triangles. OE equals to OE, it is a common side that belongs to both triangles. So we actually prove that those two triangles can go into each other by proving that their hypotenuse can go into, and we have also one side that is congruent, it belongs to both triangles, OE. We actually prove that those two right triangles can go into each other according to rule number 5. And what is rule number 5? Rule number 5 states that if the hypotenuse and a perpendicular of one right triangle are congruent to the hypotenuse and perpendicular of another right triangle then the right triangles congruent to each other. I repeat again on rule number 5. According to rule number 5, if the hypotenuse and the perpendicular of one right triangle are congruent to the hypotenuse and perpendicular of another right triangle, then the right triangles congruent to each other. Okay, and we actually proved that the hypotenuse and the hypotenuse OB and the perpendicular OE of the right triangle OEB congruent to the hypotenuse OE and the right triangle OA, to the hypotenuse OE and we actually proved that the hypotenuse OB and the perpendicular OE congruent to the hypotenuse OA and the perpendicular OE in triangle OEA. Therefore, we proved that those two triangles congruent to each other according to rule number 5. And from the fact that those two triangles congruent to each other, we will conclude that AE equals to AB, AE equals to EB. We conclude that AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides, that is to say AE and EB, will be equal to each other. So what is the value of AB? The value of AB according to the drawing, AB equals to AE plus EB. Again, for the drawing you can see that AB equals to AE plus EB, but we already found out that AE equals to EB, therefore we can substitute AE in this equality by EB. So we substitute it and we get that AB equals to AE plus EB, so it equals to EB plus EB, and EB plus EB, it is actually equals to 2 times EB, and we have already found out that EB equals to 8 over 3 times square root of 2 units, so 2 times 8 is 16, so AB equals to 16 over 3 times square root of 2 units, and in terms of numbers, AB equals to 7.54 units. So I'll repeat again. AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, AB equals to 7.54 units. Okay, and you can see it here in the drawing. Line segment AB or chord AB equals to either 16 over 3 times square root of 2 units, or it equals, in terms of numbers, it equals to 7.54 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the value or the length of chord AB, and we have here a semicircle, and inside this semicircle we have 3 circles, and those 2 small circles are identical, and point O is the center of the semicircle, and point C is the center of the middle circle, and we connected together points M and C by a straight line. MC is the distance between the centers of the small circle and the middle circle, and the distance between the centers of 2 circles that have external length between them is equal to the sum of the length of the radiuses, that is to say, it equals to r plus 2, because 2 is the radius of the middle circle and r is the radius of the small circle. And we connected together points M and N by a straight line. Actually, MN is the radius of this small circle, and because of the fact that the radius of the small circle is drawn to the point of tendency, that is to say to point N, that is the point of tendency between tangent PQ and the small circle, therefore the tangent PQ is perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, we have this radius, the radius CO, is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent PQ with this middle circle. Therefore, because of the fact that the radius CO is drawn to the point of tendency, that is to say it is drawn to point O. Therefore, the radius PQ will be perpendicular to this. Therefore, the tangent PQ will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we draw perpendicular from point M to CO. So therefore this angle is 90 degrees and this angle is 90 degrees, and we defined the touching point between the perpendicular and CO as point D. Then we know that AB is parallel to PQ, and according to the rule that corresponding angles between parallel lines are equal to each other, it means that those two angles are equal to each other. And this angle equals to 90 degrees, therefore this angle CEA will be also equal to 90 degrees. And then I draw again this quadrilateral and the right triangle CDM, and we got this drawing here. We have rule number 1 that states that the sum of the angles in any quadrilateral is equal to 360 degrees. So if we relate to this quadrilateral MDON, the sum of its angles must be equal to 180 degrees. And we have already 3 right angles, and the sum of 3 right angles is 270 degrees. So 270 degrees plus the size of the fourth angle, that is x, must be equal to 360 degrees according to rule number 1. 270 degrees plus x equals to 360 degrees. We subtracted 270 degrees from this equality, and we got that angle x equals to 90 degrees. So this angle, it is a right angle, it equals to 90 degrees. Therefore, as you can see, all 4 angles of quadrilateral MDON equals to 90 degrees. They are equal to 90 degrees. And we have rule number 2. Rule number 2 states that any quadrilateral that has 4 right angles must be at least a rectangle. Therefore, quadrilateral MDON is at least a rectangle. And we have also rule number 3 that states that the opposite sides of a rectangle are equal to each other. Okay, the opposite sides of a rectangle are equal to each other, and according to rule number 3, MN equals to DO, MN equals to DO, and we know that MN is the radius of the small circle, it equals to R. So MN equals to R, MN equals to DO according to rule number 3, that the opposite sides of a rectangle are equal to each other. And MN equals to R, we know it from the drawing, that MN is the radius of the small circle. So from this equality we will conclude that DO also equals to R. And then what is the value of CD? You can see here that CD equals to CO minus DO. CO minus DO equals to CD. CD equals to CO minus DO, but CO equals to 2 units. It is the radius of the middle circle, and DO equals to R, it is the radius of the small circle. So in total we got that the value of CD, the length of CD is 2 minus R. So we can write here that CD equals to 2 minus R. Then we focused on the right triangle CDM. We know that CD equals to 2 minus R, and the hypotenuse CM, it is the distance between the two centers of the small circle and the middle circle. It equals to R plus 2. We already found out that it equals to R plus 2, that is actually 3 units, okay? So we focus on the right triangle CDM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CM square equals to CD square plus MD square. CM equals to R plus 2 and CD equals to 2 minus R. CD equals to 2 minus R. So CD square equals to 2 minus R square plus MD square. We open the brackets in equation number 1 and we got that R plus 2 square is equal to R square plus 4, R plus 4, and R minus 2 square equals to 4 plus R square minus 4R plus dm square. Here we have R square on both sides of equation number 1, so R square will get cancelled, and we have 4 on both sides of equation number 1, so 4 will also get cancelled, and what is left from equation number 1 after we cancel those expressions? After we cancel those expressions, what is left from equation number 1 is that 4R equals to minus 4R plus MD square. Here we added 4R to this equation number 1, and we got that 4R plus 4R is 8R, and 4R minus 4R is 0, so we got that 8R equals to MD square. We took a root from this equation number 1, and we got that MD equals to the square root of 8R. MD equals to the square root of 8R. But we know that 8 is 4 times 2, so we substituted 8 by 4 times 2, and the square root of 4 is 2. So in total we got that MD equals to 2 times square root of 2R. So MD equals to 2 times square root of 2R. Here MD equals to 2 times square root of 2R. And according to rule number 3, that the opposite sides of a rectangle are equal to each other, it means that MD equals to NO. Okay, MD equals to NO, but we have already found out that MD equals to 2 times square root of 2. MD equals to 2 times square root of 2, so from this equality we will conclude that NO also equals to 2 times square root of 2R. Okay, NO, we can write here that NO also equals to 2 times square root of 2R. Then we connected together points M and O by a straight line. Here we also connected points M and O by a straight line, and we connected together points M and A by a straight line. AM is the radius of the small circle, equals to R, and MO equals to AO minus AM. MO equals to AO minus AM. And we know that AO is the radius of the semicircle, it equals to 4 units. So MO equals to AO or OA, that is R, it equals to 4 units. This is the radius of the semicircle, minus AM, that is equals to R, it is the radius of the small circle. So in total we got that MO or OM equals to 4 minus R. MO equals to 4 minus R, and we know that MN equals to R, and NO equals to 2 times square root of 2R. So we focused on the green right triangle, and we implemented the Pythagoras theorem in the green right triangle, triangle MNO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, MO square equals to MN square plus NO square. MO equals to 4 minus R, so MO square will be equal to 4 minus R square, and it equals to MN square. MN equals to R, so MN square equals to R square, NO, we already found out that NO equals to 2 times square root of 2r. So NO square will be equal to 2 times square root of 2r square. Then we open the brackets in both sides of equation number 2, and we got that 4 minus r equals to 16 plus r square minus 8r. And the square of 2 times square root of 2r is equal to 8r. Here we have r square in both sides of equation number 2, so r square will get cancelled. And what is left after we cancelled r square in equation number 2? What is left? And before that we added 8r into equation number 2. Here 8r plus 8r is 16r, and 8r minus 8r is 0. So in total we got that 16 equals to 16r. We divided equation number 2 by 16, and we found out that r, the radius of the small circle, equals to 1. So we found out that the radius of the small circle equals to 1. Therefore, here the O, that is r equals to 1, and m also r, it is r, it equals to 1. And here CD, that is 2 minus r, it is actually 2 minus 1. 2 minus 1 is 1. And then we actually proved that those two right triangles are similar to each other. That the right triangle CEY is similar to the right triangle CDM. Okay, we focus on the right triangle CEY and on the right triangle CDM, and we proved that those two right triangles are similar to each other. First of all, we know that those two angles, they are equal to each other. They are both right angles. Okay, so angle CEY equals to angle CDM and equals to 90 degrees. Then we also know that this angle, it is a common angle, it belongs to both triangles, so we can write down that angle C equals to angle C is a common angle that belongs to both triangles. Angle C equals to angle C, it is a common angle that belongs to both triangles. And we also know that those two angles, they are equal to each other according to third angle theorem. That is to say, angle CEY is equal to angle CMD according to third angle theorem. What is third angle theorem? Third angle theorem is that if you have two angles in one triangle that can congruent to two angles in another triangle, then the third pair of angles must also congruent. That is the third angle theorem, and here we actually found that those two angles, they are equal to each other, they are right angles, so those are the first pair of angles that congruent, and we have also the second pair of angles that congruent. Angle C equals to itself, that is the first pair of angles that congruent. So we have two pairs of angles that congruent in those two triangles, therefore the first pair of angles must also congruent, that is to say those two angles must also congruent. That is the third angle theorem. So we actually proved that all three angles in the right triangle, triangle CEY, congruent to all three angles in the right triangle, triangle CDM. Therefore, we proved that triangle CYE is similar to triangle CDM, according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle congruent to all three angles in another triangle, then you actually proved that those two triangles congruent to each other according to angle similarity rule. And from the fact that those two triangles congruent to each other, we will conclude that the following equality is true, that CE over CY in triangle CYE equals to CD over CM in triangle CDM. CE over CY. What is the value of CY? The value of CY, you can see from here that CY equals to 2 units. It is the radius of the middle circle, so CY equals to 2 units, and CD equals to, you can see from here that CD equals to 2 minus R, and R is 1, so CD equals to 2 minus 1, that is 1. So CD equals to 1, and CD equals to 1, and CM equals to 2 plus R. CM equals to R plus 2. R equals to 1, so 1 plus 2 is 3. So CM equals to 3 units. So in total we got that CE over 2 equals to 1 over 3. We multiply the equation number 3 by 2, and we got that the value of CE is 2/3. CE equals to 2/3, and CD equals to 1 unit, and CD minus CE equals to DE. CD minus CE equals to DE. CE equals to 1 unit, and CD minus CE equals to DE. And so DE equals to CD equals to DE equals to CD minus CE. So DE equals to CD, that is 1, minus CE, that is 2/3, and 1 minus 2/3 equals to 1/3. So we found out that DE equals to 1/3. DE equals to 1/3, CE equals to 2/3, and CD equals to 1 unit, and also DO equals to 1. It is the radius of the small circle. Then what is the value of OE? The value or the length of OE, it is actually equals to OD plus DE. OD plus DE, OE equals to OD plus DE. That is to say, it equals to OD, that is 1, plus DE, that is 1/3. And 1 plus 1/3 is 4/3, or 4 over 3. The value of OE is 4 over 3 units. OE equals to 4 over 3 units. And we have rule number 3 that states that the sum of two one-sided angles between parallel lines equals to 180 degrees. So we actually connected together points, joined together points O and B by a straight line. OB is the radius of the semicircle, it equals to 4 units. And we want to find out the size of this angle. We know that AB is parallel to PQ, and those two one-sided angles, they are located between the parallel lines AB and PQ. And we know that according to rule number 4, the sum of two one-sided angles that are located between the parallel lines, the sum of the two angles that are located between parallel lines is equal to 180 degrees. Therefore, the sum of those two angles that are located between the parallel lines AB and PQ must be equal to 180 degrees. That is to say, this angle that equals to 90 degrees plus the size of angle OEB must be equal to 180 degrees according to rule number 4. I will repeat again. 90 degrees plus angle OEB, that is actually the sum of the two one-sided angles, must be equal to 180 degrees according to rule number 4. According to this rule, we subtracted 90 degrees from this equality, and we found out that the size of angle OEB, it is actually equals to 90 degrees. Angle OEB equals to 90 degrees. Therefore, triangle OEB is a right triangle. Okay, triangle OEB is a right triangle. So we can implement the Pythagoras theorem in order to find out all the values of all the sides of the right triangle, triangle OEB. We know that OE equals to 4 over 3 units. OB is the radius of the semicircle, it equals to 4 units. And this angle is right angle, it equals to 90 degrees. And the only thing that is left to find is to find out the value of side EB of the right triangle, triangle OEB. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in the right triangle, triangle OEB. That is to say, OB square equals to OE square plus EB square. We know that OB equals to 4 units. OB equals to 4 units, so OB square is 4 square, 4 square is 16, OE equals to 4 over 3, so OE square will be equal to 4 over 3 square, EB square is EB square, so here 4 over 3 square is 16 over 9, so in total we got that 16 equals to 16 over 9 plus EB square, and we subtracted 16 over 9 from this equation number 4, and we got that 16 minus 16 over 9 equals to EB square. Here we multiplied 16 by 9 and then we divided it by 9 in order to have a common factor with 16 over 9. And in total we got that 16 times 9 minus 16 over 9 equals to EB square. 16 times 9 minus 16 is 16 times 8. Okay, this is 16 times 8. 16 times 8 over 9 equals to EB square. We know that 16 is 8 times 2, so we substituted 16 by 8 times 2. In total we got that 8 times 8 times 2 over 9 equals to EB square. Here we took a root out of equation number 4, and we found out that EB equals to the square root of 2 times 2 times 2 over 9. The square root of 8 times 8 is 8, and the square root of 9 is 3. So in total we got that the value of EB, it is actually 8 over 3 times square root of 2 units. Okay? Then we actually proved that those two right triangles can go into each other, and they can go into each other because of the fact that OA equals to OB, they are the radiuses of the semicircle, they are equal to each other, they are equal to 4 units, and OE equals to OE, it is a common side that belongs to both triangles. So we actually proved that those two triangles can go into each other according to rule number 5. What is rule number 5? Rule number 5 states that if the hypotenuse and the perpendicular of one right triangle are congruent to the hypotenuse and the perpendicular of another right triangle, then the right triangles can go into each other. Okay, and we actually proved that the hypotenuse OA and the perpendicular OE in triangle OEOA is congruent to the hypotenuse OB and the perpendicular OE in triangle OEB. Therefore, we proved that those two triangles can go into each other according to rule number 5. Okay, then, therefore, because of the fact that the two triangles can go into each other, we will conclude that AE equals to EB according to the rule that corresponding sides in congruent triangles are equal to each other. And what is the value of AB? The value of AB, you can see from the drawing that AB equals to AE plus EB. AB equals to AE plus EB. And we know that AE equals to EB, so we can substitute AE by EB. So we will get that AB equals to AE plus EB, and we substituted AE by EB, and we got that AB equals to EB plus EB, that is to say AB equals to 2 times EB. And we have already found out that the value of EB is 8 over 3 times square root of 2 units. Okay? And 2 times 8 is 16. In total, we found out that AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, chord AB equals to 7.54 units. I will repeat again. Here we found out that chord AB equals to either 16 over 3 times square root of 2 units, or in terms of numbers, chord AB equals to 7.54 units. Okay, thank you very much.